this is the last session of module 3, which is about MAC layer. And we are going to talk about, continue to talk about data transfer and also about aggregation. Okay, so before we do that, let's just quickly do a revision of what we discussed in the last session. The last session was about carrier sense and medium access. We started off the session by talking about different kinds of medium access mechanisms. We said that technologies like cellular used a more deterministic medium access mechanism like TDMA or FDMA or CDMA, where in the case of TDMA, there are dedicated time slots for multiple access for all the users. And that works very well for voice communication, which is more deterministic. And then we said that the early versions of the .11 standard and the Ethernet standards implemented this what we call as a carrier sense multiple access mechanism, where there is no deterministic time slots allocated, but everyone can sense the medium and check if the medium is free, and anyone who sees the medium free can transmit at the same time. And so there is this technique called carrier sense multiple access, which was traditionally used in the Ethernet world, and then that moved on to the Wi-Fi world as well. And carrier sense in Ethernet works using a mechanism called collision detection or CSMA-CD, where when there are multiple transmitters trying to transmit at the same time, when they both transmit, they see the medium free, they both transmit, and if there is a collision on the air, then the collision is detected, the energy is detected, and then everyone backs off. And we said that that method doesn't really work well in the case of Wi-Fi because detecting a collision over the air is harder. So Wi-Fi uses this mechanism of collision avoidance, and collision avoidance can be done using methods like virtual carrier sensing, random backoff, and things like that. We talked about point coordination function, which is basically contention-free medium access, where the medium access is scheduled by the access point. And we talked about the distributed coordination function, which is the contention-free period, where basically the contention is resolved in a distributed fashion. There is no centralized control that is actually managing the devices. All the devices kind of manage themselves in a distributed fashion. They all figure out who goes first and who goes next, and that's the distributed coordination function. We said that the DCF method is the main method that is used for contention and carrier sensing and contention mechanism in Wi-Fi. PCF has been deprecated. We talked about the concept of network allocation vector or NAV, where when a transmitter sends a frame and sends a particular frame duration, then the transmitter can reserve a bandwidth for a certain amount of time, and all the receivers that are not receiving that information can look at that and say, it looks like the medium will be busy for a certain amount of time. So there's no point in me turning on my radio and sensing the channel. So let me just set an alarm clock to wake up when the medium is going to be free again, or potentially be free again, and then I'll sense again, right? And so that is called the network allocation vector, where a device can set its NAV. We talked about that. We talked about random backoff, where basically devices would pick random numbers between a window of numbers, and then start counting down as they access the medium or as they assess the medium. And then when the device that the random number goes down to 0 first, gets access to the medium and to transmit. And we used an example of a college or a school or a classroom, where you have the professor and then multiple students, and how they all get access to basically speaking in the class by using this random backoff mechanism. We explained that in detail. Then we talked about interframe spaces. We said that interframe spaces are spaces between frames, and these are needed for the receiver to be able to successfully receive the frames and process them. But we also said that interframe spaces are also used for providing priority access. So what we said is that if a particular device, if there are two devices that are seeing the medium free at the same time, and if one device has to see the medium free only for a smaller amount of time, and the other device is required to see the medium free for a larger amount of time, then this device will get priority access to the medium. So you can use the interframe space concept to create priority access. And we showed examples of how that works. Talked about the concept of contention window and how we can exponentially back off by increasing the contention window sizes, and how random numbers are picked between the contention window, and larger the contention window, the lesser the probability of two devices picking the same random number, but at the same time, larger the contention window, more the more the overhead, the more the wait time, right? And we talked about that. We talked about an enhanced distributed coordinate access EDCA parameter set, where if the device wants to do QoS, we can again use the concept of contention windows and interframe spaces to create QoS or quality of service on the wireless link. So we talked about .11e, which allows for 4 traffic categories or access categories, and each access category could have a different arbitrary interframe space and also different contention window sizes. And so if you're, for example, sending voice traffic, you can pick a smaller interframe space and a smaller contention window. If you're sending best effort traffic, you need to pick a larger contention window and a larger interframe space, and that gives you different levels of priorities access to the medium. And what kind of interframe space and contention window each access category needs to pick is determined by the access point, and that is advertised as a part of the EDCA parameter set that is part of the beacon frame inside the access point. So we talked about that, we showed that in the capture files, and then we also did a basic demo of how QoS works and how different traffic categories get different amounts of throughput and priority. So that was the last session, and if anyone missed the session, then you can go back and basically all the videos and everything are already uploaded, so you can certainly go back and look at that. Okay, so jumping into today's section. In the last 3 sessions, we have been talking about so many things. We're talking about beacons, probe requests, responses, RTS, CTS frames, acknowledgements, interframe spaces, carrier sensing. Everything we talked about so far is overhead. It's overhead, overhead, overhead. I mean, everything is adding overhead to the wireless link. But what about actual data transmission, right? How do we make sure that we minimize this overhead? And there is a reason why we have all this overhead. There is a reason why we have beacons. There are reasons why we have management frames. There are reasons why we have random backoff. There are reasons why we have virtual carrier sensing. But actually, keeping all these reasons aside, we should still be able to send successfully a large amount of data, and we need to optimize how much data we send when we still have all this overhead, right? And so that is what we need to discuss. We are going to discuss today is how, as the protocols advanced, they went from it is okay to have 80-90% overhead because of all these management frames, because I'm not really trying to send a lot of data. So early versions of the protocols were not really looking for high throughput. In the like, if you look at Wi-Fi 1, Wi-Fi 2, Wi-Fi 3, in those days, you're not really looking for high throughput. You're looking for reliability on the wireless link, which means that you're okay with adding lots of overhead and not having so much throughput. But as the standards progressed, we started seeing the need for higher throughput and higher bandwidth applications, and applications that require low latencies. They all started being coming to the picture, and so throughput became an important factor. And we know that there is only so much medium available. So if you want more throughput and if you don't have more medium, then you need to use the medium more efficiently, right? That is the only way you can get more throughput, by using the medium more efficiently. So today we're going to talk about some of the methods that are used to try and use the medium more efficiently, while we don't lose any reliability at the same time. We still want to have all the management frames, all the beacons, all the virtual carrier sensing, all the backoffs, everything. We need all of that. But when we win access to the medium and when we send data, can we optimize that opportunity and send more data, right? And use the more airtime more efficiently. That is what we're going to talk about today. So at a very high level, if you look at the Wi-Fi, let's say airtime usage, we talked about this in the past sessions also. If you look at, this is the entire medium time or airtime available over a period of time. Not all of that is actually useful for Wi-Fi medium usage. Some portion of that goes for Wi-Fi interference, and some portion of that goes for non-Wi-Fi interference. So what is non-Wi-Fi interference? If there is any kind of Bluetooth or Zigbee or like cordless phones, baby monitors, radar signals, any of these other technologies that are operating in the Wi-Fi spectrum, they come under non-Wi-Fi interference. So when we talked about CCA, clear channel assessment, we talked about 2 types of basically detections for CCA. There is a signal detect and there is an energy detect, right? So energy detect means that we are trying to detect for energy levels of signals coming from that are not Wi-Fi signals, right? So when we see that energy at a certain level on the medium, even though it's not Wi-Fi, even though we're not detecting a real preamble of a Wi-Fi frame, we have to back off. We have to not use the medium. So some portion of the medium is gone for non-Wi-Fi interference in any wireless LAN cell that we have. And then some portion is gone for the Wi-Fi interference. Maybe there is a neighboring access point that is right next to you, that is operating in the adjacent channel or in the same channel. And so then you see signal detect, right? In this case, you're actually seeing .11 frames, Wi-Fi frames, but they don't belong to your wireless LAN cell. They belong to the neighboring cell. But you still need to stay back and not transmit. So that means that there is a portion of the airtime, medium time, that is not being used because of Wi-Fi interference. And then there is only some portion left for actual medium usage. Now again, this portion we talked about is now again broken down into data frames, management frames, control frames, as I mentioned, right? And again, as we discussed, all of this comes under overhead, and this is the only thing that is actual data transmission. Now, even the data frames airtime can actually still be broken down into multiple SSIDs. So if there is a physical access point, if there's one access point like this, it could have several networks, virtual networks, SSIDs, and so on. So that bandwidth is shared between all these virtual networks. You could have 4 or 5 SSIDs, but they're all sharing the same airtime because there's only so much medium available for this device, and they all need to share that, right? So the multiple SSIDs or multiple virtual networks are sharing that airtime. And again, under each virtual network, you could have one or more client devices connected. So there are, let's say, one or more phones, one or more devices connected, right? In that case, then you have to share the medium again between those devices. So the next time we see that this particular access point can do a lot of throughput, what comes to the final device could be a very, very small portion of it, as we discussed in the past, right? So now the question really is, how do you optimize this this particular time is really what we're going to talk about. Now, before we go there, to put things in perspective, let us look at this in a little bit more detail. This is basically showing you how much actual medium airtime you're using for data transmission, right? So if this axis is time, and this is in microseconds, this goes from 0 to 500 microseconds here. This green box is where you're transmitting your data, right? And to send this one data, you are actually using all this airtime as overhead, right? As we mentioned before. So there is the diffs. We talked about the distributed coordination interface space. That is the minimum time we need to wait for a transmission. And then we talked about contingent window, where we need to back off. And then we talked about we have to have some form of virtual carrier sensing mechanism. So we have a legacy preamble, RTS, and then a CTS frame, and then we have the data frame. But when we start sending the data frame, we have headers for this data frame. Again, we have the HT headers, VHT headers, the physical layer headers, right? The PLCP header and all of that. All of this is overhead, and then you send the data frame. And then after that, you wait for the acknowledgement, right? And this is overhead. So if you look at these blocks, there are certain blocks that are just dead air. You're not transmitting anything. The diffs, the contingent window, the SIFs, all these things are dead air. You're just not transmitting anything, right? And then all these other things which are part of overhead, by the way, they're all, of course, transmitted at legacy rates. They're all transmitted at 1 Mbps or 6 Mbps, very low data rates. So even though you're sending very less information, they're taking up a lot of airtime. So if you look at this particular example here, to send a 300 byte frame at MCS 7, one spatial stream, short guard interval, the physical layer data rate is about 72.2 megabits per second, which means that you only need about 33 microseconds to send this frame on the air. This 300 bytes, to send the 300 bytes, you only need 33 microseconds. And out of the 395 microseconds that are being used for the transmission. So which means that you have 91.6% overhead, right? Interestingly, if you look at this other example at the bottom, let us say now you're doing 2 spatial streams instead of 1 spatial stream. Same frame, MCS 7, short guard interval, you're doing 2 spatial streams. That means you're doing MIMO, 2 by 2 MIMO. Right? Now you have doubled your physical layer data rate. Now you can transmit at 144.4 Mbps physical layer data rate. This is what it says on the AP, on the box. Right? But what has happened here? What has happened here is that the frame now is transmitted in half the time, because you now have double the data rate speed. So instead of taking 33 microseconds, you take only 16 microseconds to transmit the frame. But you still have 381, you still have all these other overheads. So the total time is only reduced by 16 microseconds. So instead of the transmission time being 32 microseconds out of 395, now it is 16 microseconds out of 381. So in fact, what happened was the percentage of overhead actually increased, because now the time taken for the overhead has not decreased. The time taken for the data transmission has decreased. The overhead is all still there, which means that the percentage of time taken by the data transmission is now lesser, and so the overhead is technically even higher, relatively speaking, right? And this is the unfortunate part of the overhead. Right? Now this problem needs to be solved. So of course, as we mentioned, the data frame overhead, if you look at the overhead, as we mentioned before, it comes from all these places: interframe spaces, random backoff, and so on, things like that. Now, if you look at some interesting data, if you look at this data, I took this data from one of the papers that I found online, which actually did a lot of analysis on that. I put that in the reference section for anyone interested. But if you look at the frame sizes, so these are different 5 data rates. And if you look at when these are the 5 data rates, if you're sending a 100-byte frame data payload, and what happens if you're sending a 1500-byte frame, right? So if you're sending a 100-byte frame, when you're transmitting at 54 Mbps 5 data rate, right, your actual throughput would be only about 4 megabits per second. That means you have 92% overhead. But at the same time, if you're sending 1500-byte frames, so which means you're sending more payload per transmission, then your throughput is actually almost 30 Mbps, close to 30 Mbps. And it's your basically your overhead or your loss efficiency is only 43%. So just by sending larger frames, you can actually send and larger portions or larger chunks of frames at any given time, you can actually reduce the amount of overhead that you have in the link, right? Just like if I have to talk in a meeting, and if I have 10 sentences to say, so if I have to say, if I get my turn and I say one sentence, and then I wait my turn for again and I say my next sentence, and I wait for my turn again and then tell my third sentence and so on, there's a lot of overhead. But the moment I get it my turn, if I'm able to speak like 10 sentences, then that will of course save me a lot of overhead, right? So it's the same model. So of course, by increasing the size of the transmission, increasing the size of the frames, you can actually reduce the overhead. There is one aspect of this transmission though. So of course, when you send the data frame, there is the question really comes, okay, why don't I send like really large frames? Okay, so why instead of sending 100-byte frames, I'm saying that my throughput will increase a lot if I send 1500-byte frames. But then I can say, okay, why not send 15,000-byte frames? Why can't I send even larger frames and say even more time? Of course, there's an overhead for that. The larger the frame, the higher the chance that it would be subject to errors, or which means that it could be subject to retries, right? So let's say if I'm sending 100-byte frame and it doesn't get to the receiver, what I only lost is 100 bytes, so I can retransmit. But if I'm sending a 10,000-byte frame, large frame, and if that gets lost, even one bit error is there on the receiver side, now I have to retransmit the whole thing, right? So of course I have to put a limit on how big my data transmission has to be before I get an acknowledgement, because there is a cost of retransmissions, and the cost is actually very high, right? So for example, when we send one data frame, already to send this data frame, we are doing this random backoff and carrier sense, and then we send this data frame, and let's say that data frame did not get received by the receiver. Now what we need to do is, if you look at the picture on the bottom here, now what we do is we need to wait again. We need to do exponential backoff, which means the amount of backoff we need to has to increase, which means that we have to wait longer to get access to the medium. And after we get access to the medium, now when we transmit the data, we have to transmit at a lower data rate, because we know that the higher data rate that we transmitted at was possibly causing frame errors. So I need to rate adapt, right? And I come down to a low data rate. Now the same data frame actually to transmit on the air could take twice the amount of time. And let's say my first retry also got lost, right? So I timed out. Now it's even worse. Now my exponential backoff has increased even more. Now the amount of time I need to wait to get access to the medium has increased even more. And then once I get access to the medium, again, I most likely would drop the data rate, which means that the same data frame actually takes even longer on the air to get transmitted. So in other words, if I was able to successfully transmit the data, this is the airtime I'm taking, But if I have retries, then there is all this extra overhead, and x-axis here is time, and you have all this extra overhead. So of course you want to avoid retries as much as possible. So you have to build protection. So what the ideal outcome is, where we can send a lot of information very quickly, but also send it reliably. Because if you don't send it reliably, then there's a cost of failure, and that slows everything down again. So what are the methods we can use to try and send more information faster in each transmit opportunity we get? Anytime we get a transmit opportunity, we get access to the medium. We spend a lot of energy to get access to the medium. Now we got access to the medium. So how can I send a lot of information reliably is what we are trying to do. And those are the protocols that we're going to discuss in this session. So one method is to reduce the overhead, is something got introduced in .11e in the QoS extension. It is called basically transmission bursts, right? You can burst frames, right? That's also called TXOP. So this model is where the traditional model is where you back off, you content, you wait for the interframe space, you send a data frame, you wait for the acknowledgement, and then you go back into the queue and you go back and content for the medium, you back off and do that. That's the traditional method. In the TXOP, the transmission burst method, what you will do is you'll only content once. You content for the medium, you win access to the medium, and now you send bursts of data frames, right? You send a data frame and you wait, and the receiver will wait for a short interframe space. It will send an acknowledgement, and then you don't do any back off at that point. You only wait another short interframe space. Remember, if you remember from the last session, I mentioned if you're waiting for a short interframe space, that means that no one else will get to transmit in the middle, because everyone else has to see the medium free for at least a DIFS period, which is much longer than the short interframe space. So which means that if you're transmitting one after the other with 6 intervals, that means you get atomic access to the medium, right? So you get preferential access to the medium. And so once you do this back off and you get access to the medium, you send information in bursts. You send data, you receive the acknowledgement, you again wait only a SIFs, you send the next data, you receive the acknowledgement, and keep doing that until your transmission opportunity expires. So how long you have the transmission opportunity is something that is predetermined as a part of the protocol negotiation. And this will basically save you so much airtime, right? So this is one of the basic methods that are used, right? And then there is this concept of aggregation that we're going to talk about as well. Now, before we talk about aggregation, I need to explain how aggregation is even possible. Like, so one of the things that happened over the various standards as the standards evolved is we started improving on the speeds, meaning the MCS rates, the modulation coding rates, the raw data rate at which we can transmit frames has consistently increased with every standard, right? Because of that, the amount of time taken to transmit a single frame has decreased substantially. Right? So if you look at this particular example, if you are using a BPSK, very low order modulation rate, 1/2 coding, you are transmitting at a physical data rate at about 65 megabits per second. Now, at 65 megabits per second data rate, it takes about 184 microseconds to transmit a 1500 byte frame. So normal .11 frame is 1500 bytes approximately. So it takes 184 microseconds at that speed. So now as you increase your speeds, now if you came from 65 to 650 megabits per second at 64 QAM modulation rate, now within that same time slot, you can send 10 such frames. So what we are saying is, okay, in the older standards, I got access to the medium, I send 1 frame, and it took me 180 microseconds, and then I went into back off again. But now with the newer standards, once I get access to the medium, if I can keep the 185 microseconds for me, I can actually send 10 frames because my transmission is much faster now, right? So because of the increase in speeds, that enabled this concept of aggregation, where you can say, okay, I got access to the medium, let me burst and send a lot of frames one after the other, because I don't need a lot of airtime. So one of the things that we need to realize is airtime, or the amount of time taken on the air, is directly related to the probability of error. The more time you transmit, right, without you knowing if the receiver is receiving it, the more probability of error. Because if you're taking long airtime, that means that the channel conditions might change over a period of time, and so the errors might happen. So you don't want to, so transmitting a packet in the air is like flying in blind without having any, or driving blind without having any eyes, right? If you close your eyes and you drive, you don't want to drive for very far, right, on the road. The farther you drive closing your eyes, the more chances you have to be in an accident, right? So transmitting and using the airtime is just like that, without having acknowledgement. So what we're trying to do here is, we want to restrict the amount of airtime we take to transmit without waiting an acknowledgement. But if we are able to send more information within the airtime, then we can aggregate. And then we, without increasing our probability of error, we are increasing our throughput, right, by using this method. And that is where aggregation came along, right? The concept of aggregation came along. So if you look at the various methods that have been introduced in .11e and .11n standards, so of course in .11e we came up with this concept of data bursts. I talked about that, where you send a data frame, you get an acknowledgement, immediately you send another data frame, and you get an acknowledgement, and so on. Right? And then .11e also introduced this concept of basic aggregation, where you send these data frames one after the other, and instead of waiting for individual acknowledgements for each frame, what we do is we wait for this concept of what we call as a block ACK. So block ACK is nothing but I send like 3, 4, 5, 10 frames one after the other, and I'm not waiting for acknowledgement, right? And then at the end, I'm going to send a request to the receiver saying, hey, can you now acknowledge all the frames that I just sent you? And the receiver will send a block acknowledgement. And inside the block acknowledgement, there will be this bitmap that will allocate 1 bit for each frame that was sent. And it will say, okay, you send me like 10 frames, and I received frames 1, 3, 5, and 8, right? And I did not receive 2, 4, and 6. So that's what the block acknowledgement will tell the transmitter. And then the transmitter will say, okay, so whatever you received, you can keep them. Whatever you did not receive, I will retransmit them in the next batch of frames that I'm going to send, right? And that is basically how aggregation works. And then in 11n, there are other methods that are introduced to something called as a reduced interframe space, where you can actually pack the data frames even closer. And then there is also there are concepts like immediate block ACK and the delayed block ACK and implicit block ACK, and all these other different methods that are created, that are all variations of the same concept of bursting data and then receiving the acknowledgement, and basically trying to improve your medium utilization and your efficiency of the channel. So in simple terms, the concept of aggregation is a lot like you have a lot of people that you want to take from point A to point B, and you need to transport all of them. So assuming each person is a packet and you want to transport all of them, one method is you can put each person in one car, and you can put them on a highway, and every person will take up one car, and the highway is full of cars, which means that the person is only occupying like 10% space within the car, and the person only weighs 10% or 1% the weight of the car. So that all the weight of the car, the volume of the car, everything is all overhead to transport this one person, right? So you can either do it this method, where you can put one person in each car and take up the entire highway and entire bandwidth, and basically cause traffic congestion, or you can put those of you, my friends who are from India, you might relate to this example. You may have seen this at some point somewhere, where you can put a lot of people on a single vehicle, right? This normally doesn't happen. It's just for fun, I put this picture. But you can put like all these people on a single vehicle. In this case, it's a train, and then you can transport them. Now you're getting a lot more efficiency with using one vehicle or one set of overhead, and there's barely any overhead here. There are more people than the metal in the train, right? So so this is what aggregation does. Aggregation transports a lot more information in one container and in one set of overhead, and then it improves the efficiency, right? This is a kind of a basic example of that. So frame aggregation, again, to explain it in a slightly different way, this is your normal method where you wait diffs, you do a back off, and then you have your frame header, and then you send a data frame, and then you wait a SIFs, and then you get acknowledgement, and there are multiple transmissions here. Now you're taking all these payloads in this entire communication. All these blocks in yellow are the only ones that are the payload, the actual transmission. So you take all 3 of them and put it in one burst, and then you only do one diffs, one back off, and then you transmit, and then you wait for acknowledgement, and now you save so much airtime, right? So that's basics of frame aggregation. So when it comes to frame aggregation, there are two types of aggregation that frame aggregation that are normally used, or we call it as AMSDU frame aggregation. MSDU is nothing but the max service data unit. So this is your you can call it up as your IP packet, so including the IP header. So that's your max service data unit. And then you can aggregate at that level. So meaning you can take multiple IP packets and multiple MSDUs and put them together, and then apply one MAC header to it, just one MAC header, and then send it to the bottom layers, right? And then that is going to the bottom layers, and then it becomes the protocol PPDU, where you add the PLCP header to it, right? So basically, MSDU aggregation is where you take multiple MSDUs or IP packets, put them right next to each other, add one MAC header to it, and then send it down to the layers, and then you have another physical layer header on top of it, right? So that's how MSDU aggregation works. AMPDU aggregation, on the other hand, is where you take individual MSDUs and you have individual MAC headers for each MSDU, and then you take all of them together and then put it in one aggregate, right? And at the physical layer, it's still one large frame, and then you put one physical layer header for all these things together. So of course, this is a little bit more overhead than this one, but it provides a little bit more protection, right? So these are the two more common methods of aggregation that are used. At the end of this session, if you have time, I'll try to show a short demo of these things. Again, to kind of summarize the types of aggregation: no aggregation, physical layer header, MAC header, data frame, and then the transmission goes this way. If you're doing AMPDU aggregation, then you have basically each MSDU will have its individual MAC header, but they'll all be clubbed together with only one physical layer header. So you've saved all these physical layer headers. You've removed all the physical layer headers. You removed all the random backoffs and everything, and you clubbed all these basically individual MAC headers and MSDUs into one MPDU aggregate. So this is obviously more efficient. But if you're looking at AMSDU aggregation, you're removing these extra MAC headers also, and then you're clubbing these data frames together. You're only having one MAC header, and then you have one physical layer header, and it's even more efficient. And then the last method is where you can combine both, where you're doing AMSDU inside AMPDUs. So this is has a little bit more protection. So let's assume that this is one AMSDU where you combine two things, and then it will have its individual MAC header. So every 2 MSDUs will have, or every 5 MSDUs or 10 MSDUs will have one MAC header, and then they will be clubbed together into a AMPDU, and then they will all have one physical layer header, right? So this is another kind of a hybrid model where you are combining both MSDUs and MPDU aggregation. So these are the different methods used. Again, the more you aggregate and the better method you use, the more throughput you'll get, the better the airtime utilization is, but the more error prone the link is. So as a simple example, if you lose MSDU3 here, let's say you're transmitting it in this particular case, if you lose MSDU3, then you only have to retransmit this frame in this particular case. But if you're doing AMSDU aggregation, if you lose MSDU3 for some reason, you have to retransmit this whole thing, right? Because that's all lost, right? So of course, the probability of error or the cost of error is going to be higher, right? But the fact the matter of why we are doing this now and why we were not doing this in the earlier standards is because of these reasons. It's important to understand the reasons. As the standards evolves, the transmitter and the receiver got better and better. The quality of the transmitters received got better and better. The ability to deal with noise got better. The ability to deal with lower SNR conditions got better. The speed at which you can transmit has gone better. So which means that the probability of error has gone down as the technology started improving, and which means that we will be able to afford to do these kinds of things in the newer standards. And we use that as an advantage to actually do this in the newer standards. Okay, so coming back to this concept of the block acknowledgement, as I mentioned before, the normal process in which this works is the transmitter basically would, if it wants to initiate an aggregated transmission, it normally uses this block ack mechanism, or it basically sends this frame called add block ack or add BA to the receiver. It sends a request, and if the receiver is capable of receiving aggregates and it's capable of doing block acks, then it will send an add BA response or an add block ACK response. And the transmitter will know, okay, the receiver is capable of doing block acknowledgements. And the receiver will also tell what type of block acknowledgement it can do. It can do immediate block ACK or delayed block ACK, or what type of acknowledgement it can do. So once the transmitter and receiver know each other's capabilities, then the transmitter will start bursting the data. It will start sending QoS data frame, data frame, data frame, data frame. And after it sends a bunch of data frames, then it asks for the block ACK request. The transmitter will say, okay, I send like 50 frames now. So now can you send me an acknowledgement? It sends a block ACK request, and the receiver will send a block acknowledgement, and then this is what you see inside the block acknowledgement. So inside the block acknowledgement, you just have this bitmap, and there are two things here in the block acknowledgement. One is the starting sequence number, and another one is the bitmap. So for example, in the first scenario, let's say the starting sequence number is 1, and the bitmap has 64 bits, right, to it. So if all these bits are set to 1, that means that we are saying that from frame 1, sequence number 1, I received all these frames up to 65 successfully. And that's what the block acknowledgement is telling the transmitter. When the transmitter receives this block ACK in the bitmap, it will say, okay, all the 64 bits are set to 1, which means that all the 64 packets that I send or frames that I send were successfully received. Okay. So now in the next sequence, let us say, now the starting sequence number in the next sequence of aggregate is starting sequence number 65, right? And now you see that you have an again block ACK bitmap here, and there was like one of the bits was set to 0. So if you do the calculation, it is basically bit number 61 from the starting sequence number 65. So if you do the calculation, the receiver will know that frame number 126 is lost, because that is not acknowledged. There's a bitmap is set to 0, right? Which means that sequence number 126 is lost. And you're telling the transmitter that I received all the other frames, but I did not receive the acknowledgement for, I did not receive the, or I did receive it, but there were some errors. Remember that each one of these frames also have an error check mechanism. So the receiver will actually check the errors on each one of these individual frames. And if any one of those errors are wrong, the calculation is wrong, the FCS is wrong, then it will say that frame is not received. Right? And so that information is sent to the transmitter, and the transmitter in the next batch of frames it is sending, because it has to send from 129, but it will actually retransmit 126, because 126 in the last batch got lost, and it will retransmit, right? And again, the block acknowledgement will check the starting sequence number, and it will acknowledge everything from the starting sequence number, and that process will continue. So now what we are doing is we are using a way to acknowledge a large number of frames in one block, and that's why it's called block acknowledgement. And by using the bitmap, we can actually tell by allocating only one bit per frame, which reduces your overhead a lot. You can tell if that particular frame is received or not. And that's how the concept of block acknowledgement actually works. And then we have there are concepts like delayed block ACK and immediate block ACK in Wi-Fi. So immediate block ACK is nothing but where you send a burst of data frames, and then you send a block ACK request immediately, and then the receiver will send a block acknowledgement immediately. So which means that the receiver needs to process that very quickly. It looks very simple when I say it, but there's a lot of computations that are going on behind the scene. You just send 64 frames to the receiver. The receiver needs to process all of them, do all the error calculations, everything in each one of them, and collect all the data, and then create the block ACK acknowledgement within a short interframe space, within a few microseconds, literally. So the receiver's computation power should be really, really nice. And this is why this is all done in hardware, right? And the reason why you do this in hardware is because you have to be very, very fast. And again, the reason why we're able to process so many frames all at such a high speed is the technology has improved exponentially. Our ability to basically tolerate errors, our ability to compute more computations, all has increased, which means that now we're able to, within a few microseconds, able to process all these frames, compute the block ACK bitmap, and transmit it. And if that computation power is not there, then this technology will not work at all, right? So immediate block ACK is where you send the block ACK immediately after you do the computation. This is used for delay sensitive traffic. Anything that has needs low latencies needs to be acknowledged immediately, right? Otherwise it's going to be a problem, because the transmitter also needs to buffer those frames. If you don't give an immediate block ACK, which means the transmitter needs to save those frames that burst, assuming that one of them could be lost, right? As soon as it gets the acknowledgement, then it can drop that from its buffer and buffer its next set of frames. So it will delay the process, right? If you're using a delayed block ACK. So the delayed block ACK is where you send a burst of frames, you send a block ACK request, the receiver will just send a normal acknowledgement, and then after a while, at some point, after it does all the computations and everything, it will send a block acknowledgement. So that's a delayed block ACK mechanism. So one of the things I'd like to show here is basically the effects of aggregation on throughput. Again, this is one of the I took this one from one of the research. I don't know if it's a research paper. Someone did some analysis on this one, which I thought was pretty cool. I put it in the reference list here. But if you look at how aggregation affects the throughput, you can find it very interesting here. So, for example, if you look at this table, I used some examples of 11N, 20 megahertz, one spatial stream, 11N, 20 megahertz, two spatial stream, three spatial stream, four spatial stream, and then I went to 40 megahertz and so on. You can see as we increase the channel bandwidth and number of spatial streams, the physical data rate will increase, right? As the physical data rate increases, this table shows the wastage of medium without aggregation, and this table shows the wastage of the medium with aggregation. Right? Now, one of the things you will see is the maximum advantage you will get with aggregation is at highest speeds. This is a very fascinating thing. The higher the speed, you see that without aggregation, you have 91% overhead, and with aggregation, you only have 21% overhead. Right? Why is this the case? Right? It's a very interesting thing. So if you look at this analysis that I've done here, let us take one example of where you're transmitting at low 5 data rates. The data packets itself are being sent at low data rates and without aggregation. So this axis is time and this axis is data rates, right? And if you look at that box there, that is your available medium. So many times people calculate medium in terms of time, but actually medium is two-dimensional. There is time axis and then there's also the data rate axis, right? Because that is the amount of bandwidth available in terms of data rate. So when you're using legacy, all these overhead frames like CTS, RTS, basically all your interframe spaces and all these other things that you're transmitting, they're all transmitted at very low data rates, right? If you go back to that example that I showed you here earlier, all of these, you can see that these are all transmitted at low data rates. This example here, everything here is all transmitted at legacy rates, right? RTS, CTS, and all of that. That overhead will not change; it will stay the same, right? The only thing that can change is the speed at which you transmit your data frames. So now, if you look at this example, low 5 data rates without aggregation, this is your data. This is your basically your data, and everything else is your overhead, and this is the wastage of the medium, right? Now, if you do the same thing with low data rates, but with aggregation, now what you're doing is you're sending, you're taking more time, which means you're sending more data, but you're still sending them at low data rates. So there is still a lot of wastage here, right? In this particular case. On the other hand, if you're sending at high data rates, right, on this axis now you're sending at high data rates, and this is your amount of throughput you're getting without aggregation, and then you're sending at high data rates with aggregation. In this particular case, you'll see that you're getting a lot more medium utilization and a lot less medium wastage, because every time you're getting a transmission opportunity, you're not only sending more, taking more time to send the data, you're also sending more data, right? And so the wastage is a lot lesser when you're aggregating at higher data rates when compared to aggregation at lower data rates, which is a kind of interesting study. That paper, if you read that, it will have more details about it. But in other words, what we're trying to say here is aggregation is really very useful in the modern standards, where you're using in the 11AC, 11AX standards, where you can transmit at much higher speeds, and that is where you get the most bang for the buck. That's where you get the most efficiency, right? When you're doing at lower standards, lower speeds, even though that you're aggregating, your efficiency is going to be still lower. And then there are other mechanisms, right? There is other mechanisms like admission control that was part of .11e, and here we are not trying to improve the medium utilization. What we are trying to do here is we are trying to be more careful about who we are admitting into the network. So let's say there is this access point that is already serving a lot of clients, right? And it already has a lot of medium utilization. And if there is a new client that is coming to connect to it, the access point can actually choose not to connect, allow that client, right? That's one method. But the other method here in admission control is, let's say there is a client that's already connected to the access point, and he wants to request for a certain amount of medium time. So basically, it is asking for a transmission opportunity, right? And the station will say, I want to do an add TS or a transmission op. I need some. I need to add a traffic stream, right? And then this is my requirement. So I want to be able to send this much amount of data for this much amount of time, and I want so much medium. So the station can request the AP, and the AP will check its current load, and it says, oh, okay, I have too much load already. I have many devices that are connected. I really cannot accept this request at this point. And so it will reject that request, or it will accept that request, and then the station will get to transmit. So this is one way of controlling admission into the network. This is a lot like if anyone who's used to this concept of basically priority access to the highways. Normally, you have these the lanes that are there where you have traffic lights to enter the highway. So basically, when you want to enter the highway itself, you want to slow down the number of cars that are entering the highway, because the more cars you admit into the highway, the more congestion you'll have. So in the morning, normally in the busy hours, there is separate traffic lights on the side roads that will only admit a certain number of vehicles into the highway, right? So that's called admission control. So you want to minimize the amount of traffic that is getting into your network to actually get better utilization. So there is a concept of admission control there. There's also something called as QBSS element that is part of 11E, where when the client is connecting to the access point, the AP will advertise in its beacons its load parameters, right? It will tell that I have so many clients connected to me right now, and I have so much medium utilization, right? So when the client is connected to the AP, it can make a decision based on that. So this is like similar to the example I gave in the past, where you are in the airport and you're basically in the food court, and you go to each food stall and you say, okay, there are already 10 people standing here in line, and so there's a very good chance that I will not get my food on time and I might miss my flight. So let me go to the next stall, right? So similarly, you can look at the QBSS element inside the AP's beacons and say this AP is already quite loaded. It's already serving lots of devices and has medium utilization. So let me go find some other access point. So this is another way of controlling the admission, and so that the whoever is already in the wireless LAN cell can get better access to the medium, and that is another method that's used. So that is basically a quick summary of all the things that I was talking about, aggregation and things like that, and how aggregation works, different types of aggregation, block acknowledgements, how to use the airtime better, AMSDUs, AMPDUs, and so on. So since we have about 5 minutes or so, I thought we'll show you a quick demo of how the throughput will vary with different levels of different types of aggregation, right, and different types of standards. So the demo is very straightforward. So basically, I have some of our candle equipment that is acting as a traffic generator, and the same test equipment is also creating these virtual stations that are here. So basically, there's one piece of test equipment that is creating the traffic on the wired side, and the same test equipment is also creating wireless clients on the wireless side, and then we have this access point in the middle, and we're trying to run traffic, and we create different types of clients, and we will see how aggregation will increase throughput and how much effect it has in throughput. And the router that I'm using here is basically a VNCD into my box here, and I'm using this ASUS gaming router. It is a Wi-Fi 6E router here, and I'm using my test tools. Let me just quickly show you here. So we created 4 stations, one 11A station, which is a legacy station that is doing 20 megahertz 1x1 MIMO. And we created one 11N station, which is doing 40 megahertz 4x4 MIMO. And then we created one AC station that is doing 80 megahertz 4x4 MIMO, 11AC. And then we have another AX station that is doing 80 megahertz 4x1. We can see that the 5 data rates will change based on the standard. If it is 11A, the maximum data rate you can get is 54 Mbps 5 data rate. If it is 11N 600, 11AC is 1733, and this is not this is only 2x2 actually. It's not 4x4. Oh no, it's 4x4. This is not right now, but when you run the test, it will be correct. So there are 4 types of stations available. And then when I run some traffic, I'd set up individual traffic streams to each station. So when I am running traffic to the 11A client, the legacy clients, I'm going to start this traffic stream. Remember that 11A does not have aggregation, right? So we cannot do aggregation. So we are getting about 27 Mbps throughput here, which is what is expected. So it can do maximum 54 Mbps. If you take out all the overhead and there is no aggregation, if you're doing large frame sizes, you're getting about 27, 28 Mbps. And now if you do a simple packet capture on that link, you can see this is real time while I'm running the test. You can see that there is no aggregation here. There is one data packet, and then there is one acknowledgement. Then there is another data packet. There's an acknowledgement, one MSDU at a time, no aggregation, right? And this is being transmitted at 54 Mbps. You can see the data frame is transmitted at 54. The acknowledgement is transmitted at 24 Mbps because the acknowledgements are transmitted at lower data rates, right? So this is simple throughput without aggregation. What happens if I do 11N? So 11N added this concept of aggregation or AMPD aggregation. So let's say I stop this traffic stream and I start this one, 11N. So this 11N is actually 4x4 MIMO. So it is capable of doing up to 600 Mbps, I think 5 data rate, if I'm not wrong. So, or maybe 800. So, and then this is the throughput we're getting. We're getting about 215 Mbps throughput on this link. So now if I do the same packet capture here, do a start capture here. Now it is doing aggregation. See, you can see all these MSDUs. It is not doing AMSDU. It is only doing MSDUs. And all these MSDUs are part of one AMPDU, right? So these are all clubbed together, and they will all have individual MAC headers. If you look at any of these MSDUs, it will have its own MAC header, right? But it will all together have only one physical layer header at the end, right? And then at the end there will be a block ACK. So you can see that there is a block acknowledgement. This is the receiver sending the block acknowledgement. This is the block ACK sequence number, starting sequence number, and also the bitmap. So this bitmap is here is in hex. Of course, all Fs means that it's all ones. So that means it received all these frames successfully. So none of these frames need to be retried. And so the transmitter will send its next set of frames, and then you wait for the acknowledgement and so on, right? So this is your AMPDU aggregation model. Now, then later standards like 11AC and 11AX started enabling AMSDU aggregation also. And we started doing AMSDU aggregation. So if you start this traffic stream to 11AC, for example. So now 11AC is doing, it can get higher throughputs. Now you're getting almost 700 Mbps throughput here because it's using higher modulation rate. Basically, it's using like MCS 9 and so on, which is going up to 256 QAM and other higher data rates. And so now you're getting higher throughput. And now if you do a packet capture on the same link, I'm starting the capture again. This time the 5 data rate is even higher. It's 975 Mbps. And now the aggregates are also much bigger. See, you can see because your data rates are higher, now within the same time, you're able to send more data. So now the transmitter can pack more information. You see large aggregates are being built. And then you have one block ACK. You see in the middle, you'll have some block ACKs here. So there's a block ACK here, right? So there is larger aggregates that are being sent at a higher data rate. Now in the previous case, it was the data rate was some 400 something Mbps. Now it's about 900 Mbps physical data rate. And now you're not only able to send lot of frames, you're able to send them at a higher rate also, right? And now this standard also supports AMSDU. So now you have, if you look at the header here, there's a separate AMSDU header also, right? So there is let me go to that portion here. So you see that it says it's an AMSDU aggregate. There is the first AMSDU subframe, and in this case, it's only doing one AMSDU, one MSDU and an AMSDU. But if you do multiple MSDUs in AMSDU, you'll see multiple subframes here. It shows only one subframe, but there could be multiple subframes here. Right now, on the transmit side, on the Ethernet side, we are fixing the size of the MSDU. That's the reason why it's not building large AMSDUs. But this is how AMSDU aggregation works, and also you can pack more data rates and send more information, and you'll get a much more efficient throughput. And now you see you can doing about 700, 800 Mbps throughput, right? If you stop this and start the 11AX one, you'll probably get even higher throughput, because this will support even higher MCS rates and also maybe even higher amounts of aggregation. And that is also something that you can run. See, it's going way past 800. So the Ethernet side, it's only limited to 1 gigabit per second. So this will not cross 1 gig. But if the Ethernet interface is more than 1 gig, then this can go up above a gig, basically. So that's a quick demo of how the aggregation works in the real world. There are lots of nice packet captures and analysis available. I put some things on the references. I can send more information later in the WhatsApp groups. So just to summarize, we covered basically the concept of how to improve the medium utilization in Wi-Fi. The fundamental main concept is aggregation. We have this concept of frame burst. We have this concept of block acknowledgements, immediate block acts, delayed block acts, and we talked about AMSDU, AMPD aggregation, and we talked about how higher speeds can make aggregation work more efficiently, and we showed a quick demo of the system. So that's it for this session. Hope you found this useful, and over to the team here for the Q&A.